Yes. Thank you, Ray, for the introduction. So the topic is this is a joint work with Arnab Bhattacharjee. This is related to my master's work, so this is not recent. So okay, so let's get started. The definition of weak expectations. So let's consider a unital sister algebra. A fits inside each. Weak expectation of A is a unital completely positive map. So weak expectation is a completely positive map phi of each to double commutant of A. So it's double commutant of A is basically the strong operator closed as well as weak operator closed. Closed under strong operator topology and weak operator topology is such that when E is restricted on A, is basically identity of A. And if sister algebra A and sister algebra A is said to be have weak expectation property, so A has weak expectation property if for every faithful representation pi of A, pi of A has weak expectation. And multiplicative domain of M is ignored by M of P. Find by H such that AB Ah, I was question. Yep. It is technical.
Arnab, is it that pi is a weak expectation or pi of a has a weak expectation?
Is a weak.
Thank you.
It is both the left multiplicative domain and the right multiplicative domain. E and A. Now, by construction, we can say this, by construction of this weak expectation map, we can say that E is even only so this is the little introduction definition about this weak expectation property. And now we will have some motivation towards the main part of this talk. So let's start with the classical situation. So the following given. Let's consider a discrete group gamma. Gamma is a discrete group. Then number one, gamma is amenable. Two, this group is algebra. Here, has great like P and the group on one algebra is injecting. So here in this classical results, we will concentrate on these two guys. So here we have this result for the discrete groups, and this which is not true for the general locally compact group. I mean, Alan Cohn already shown that for the connected locally compact group, the sister reduced group sister algebra, reduced group sister algebra is nuclear, and the group von Neumann algebra is injective, whereas it is not necessary to have this amenability condition. Now, the point is to how to use this characterization and go for the generalized case, that is for the quantum version. So that is the whole idea to connect the weak expectation property of discrete quantum group algebras with the amenability of the discrete quantum group. So this is the point we want to make. So let's start with some definition of the quantum groups. So yeah, I mean that if my group sister algebra is nuclear, then it automatically shows that it's weak. It has weak expectation property. But yeah, yeah, yeah. So what's your question? The connection there. Yeah, I mean every for every sister algebra A, if it is nuclear, then it has a weak expectation property, but converse is not true. To have this converse, you should have the exactness. Then it will help you to go other way. So one way is correct, and the other way is you have some conditions. What is the example? Yeah, I mean, if your group sister algebra is nuclear, then it's automatically you have this weak expectation. For example, here you can have this for the discrete groups.
You want an example of weak expectation, but not
yeah, then it should be. Yeah, I mean, what I'm trying to say is nuclearity automatically implies you this weak expectation. But for going from here to here, you need exactness. For
weird representation.
yeah, it works for the faithful representation. So, I mean, it's sufficient to have a non-exact, but which has weak expectations, so something like that. Okay, so this is denoted by G, which is consists of system algebra A and the product delta. Also, some for notational purpose, we can A to B C on product. This is co-associativity. So is delta C of G. This is the closed linear span. So this is my compact quantum group, and if I have some brief description about the irreducible unitary representation. So if phi be irreducible representation, so all the irreducible unitary representation in compact quantum groups are finite dimensional. And it's basically comes from the, I mean, if you look into the compact topological group G. So let's, for example, take G to be like that. We know that the irreducible representation here are the finite dimensional one. So just compare with situation A to B, C here B, and we have this. We represent this pi to be the matrices. Same thing we will have for the quantum groups here also. So yeah. Let's move pi b. So pi is the irreducible unitary representation of G, and U pi b its representative. And here I will write U pi as like exactly like this. So U pi is an element of finite dimensional matrix in B pi like summation Two dimension and also satisfies so these are Swedler notations. And since we are comparing with the classical situation here, we also have the Peter-Weyl decompositions and Peter-Weyl theory. So we can use this matrix coefficients to build up an algebra. It's the same we do for the classical situation, and we write it down on like this polynomial of G is basically as spanning of U I J is from the irreducible of G. This is finite dimensional, so we can this so IJ is from of should right. So we are considering all the irreducible representation, and we are using this the coefficients, matrix coefficients, and which gives us this whole algebra and is the pointwise multiplication, because these are the elements of C of G. And same as the classical thing. So if phi 1 and phi 2 are non-equivalent, irreducible representations, representation of P. Okay, I should write it for the classical G. Then these classes are disjoints, I mean orthogonal to each other. So this phi of phi 1 of phi j, where I j from 1 to in phi 1 orthogonal to I j 1 to up to in 2. So same thing here we have for the discrete for the compact quantum group, and we write this into G as the sum of this guys. Right, is coming from the irreducible representation of G. So this is the short description of this compact quantum group. Let's come to the main point, the quantum group. And I will show an explicit example regarding this, how this quantum group works. Context. So here, as the similarly for the compact quantum group, I denote it by G with some hat, which denotes the dual of this compact quantum group. So let's find it. So this A hat.
So is it worth pointing out it's orthogonal with respect to the inner product from the Haar state?
Yeah, so it's
Because it seems to be, it's not orthogonal with respect to the algebra.
no. So when you have this your irreducible representation of non-equivalent. So I mean, as we have in the classical setting, so you have this spanning set and this spanning set. So these two are orthogonal to each other. So same situation we are trying to have for the compact quantum groups.
Yeah, using the Haar state.
Using the Haar state, yeah, exactly. So maybe I should write it. The hat is defined by this is the general definition. So this is the C-star algebra, and we also have this algebraic counterpart. So in the compact quantum group case, this was the algebraic counterpart, and I will show how this related to. So this is the algebraic direct sum of this P of H. So here we are considering the finitely many blocks. So this is the algebraic direct sum. For example, a quick example. Right. So this is my compact quantum group and was denoting by C of G and delta. So C of T can take the reduced group sister algebra. So this is my reduced group sister algebra and of gamma discrete group and co-product defined by lambda G and polynomials of G are basically the C of gamma and lambda G's. So you take the sister norm on that and you find this sister algebraic version of this the underlying algebra. So this is the algebraic version and this is the sister algebraic version. And now what about this G hat? So this should be so this is the group algebra of gamma. So A hat should be the function algebra of this. So I could take that C0 of gamma. And it should be CC of gamma. This is the algebraic counterpart of this guy, where you are taking the finitely many objects and the irreducible representation of this G here will be the gamma. So here you can see that the representations are all so the block you are getting is one by one blocks. So this is one by one blocks. It consists of lambda things.
With the algebraic one, would it be C00? The algebraic one.
So you're taking the direct sum. Yeah. Is it C0?
C00, no. I mean, finitely supported.
So C00 is finitely supported.
Is that what you'd want?
Yeah.
Thanks.
Yeah. Oh, sorry. Thanks. Yep.
So that's what the TV, if it's described the same thing. I mean, all right.
But this is finitely supported. Yeah. And yeah, CC also. Yeah. So Okay, so there is a fundamental representation of this compact quantum group. W is equal to sum of E one. You can check W is in unitary element of multiplier algebra of this. Okay. Here I also should use the notation. A with the same the unitary condition. So you're taking all the irreducible representation here. So W has to be the infinite dimension. Now, why I need this? I will need this to define the regular representation of regular representation of this G hat. So but before that, how this delta is coming? So this co-product on A hat I should mention. So even Voronovich and Podlesh showed that. So Voronovich. There exists a unique star homomorphism delta at your in that was that the happens and even this they also show this delta hat it can be explicitly written in terms of this W, like in this case, W star or X. Okay. So now. And also, I should also define this guy. So L infinity of G hat. So I have defined the sister algebraic counterpart of this discrete quantum group. I should also define, because I will need it, so the von Neumann algebraic counterpart. We have, so the underlying algebra is we defined infinity. We have for this is representation pi and bigger pi. Why we need that? Because if we consider omega hat to be pre-dual of this time, we have now we define the regular representation. We have it following way. So lambda hat from, so this is L1 of G hat, L1 of G hat to to G, and this, so L2G and L2G hat has isomorphic because they are isomorphic under the Fourier transformation due to Fourier transformation. This is defined by lambda hat omega omega hat identity. So here, I mean, in the example, you see that if in that example, if we consider reduced group system algebra, and here we know the construction of W is basically you are taking all these irreducible pi's. So it is, so my W is basically the matrix, the bigger one, which consists of all the elements from C of G. So it's basically boils down to to the classical situation. I mean, you can compare using this definition and this example, how things are compatible in the regular representation of this discrete group gamma by using this example and that definition. Because we are using this regular representation because we know we defined in the classical settings the reduced group system algebra with this regular representation, and similarly we can define also here in the discrete group the reduced group system algebra of G hat. So this is in the similar way. So reduced discrete quantum group algebra this reduced. We had number had L1 we had the norm P of L2G. I have 10 minutes. Okay, so what is the target of in this context is so classically we have this form. Classically, right now I will talk about classical things. So if phi lambda is from P of gamma to P of L to gamma presentation, and we consider a weak expectation. We consider a weak expectation P from P of H5 should be L to gamma to this reduced gamma double commutant, which is L of gamma. So we have this picture. So P of L to gamma is reduced gamma double commutant is L of gamma. And we have canonical trace from here to C. So this is my canonical trace. C. So we have this map eta from composed P. Now we know that this L infinity gamma is contained inside G of L to gamma. So we are restricting our eta on this L infinity gamma. See. So what I'm trying to say is, if we have weak expectation property in the classical settings, then we can from here to we go to the amenability condition by using this trace property. I mean, here we're trying to prove this is invariant mean, but in the quantum settings, this might make some difference. So so in the quantum settings, we will replace this by hard. Now in the non-cat type condition, it's not tracial. So what we will do? So here is the context of this talk. So the main idea to define quantum weak expectation to recover from this problem. So in the non-cat type case, what we do some trick. So the trick is for the non-catch type. Non-catch type means my hard state is hard, meaning hard state is special. But we have this this privilege in the classical setting. So what we do is we consider this condition P of L infinity of G hat contained inside the center of this L infinity. So this is basically my volume counterpart of compact quantum group. So we define formally quantum weak expectation. So this is a unital completely positive map, UCP map. P of LHE to reduce system computant such that P X is X when you restrict it to the reduced group sister algebra and satisfying the above condition. P of L infinity G hat contained inside Z of L infinity. And the benefit is, so this definition is also motivated from the definition of quantum injectivity, and it was given by Soltan and Weisselter some years before, and from there we have this motivation to define this quantum weak expectation. So what is the benefit of that? Benefit is we can actually connect this thing to the amenability. What is amenability in discrete group? So we will have the same idea as we have in the classical setting, the invariant mean. So an invariant mean on you have is a state. M is a state. It is M belongs to L infinity at start and satisfying M of the hat hat X the hat of 1 is the identity event and M of X. So X is my 0 P hat omega hat is from or hat omega hat is from the pre-2 one. So again, if you take this condition and compare with this example, you can have this amenability, I mean the invariant mean condition for the discrete groups. So amenability is the existence of such invariant mean. Is the existence now the result which is relevant to this is we have managed to prove that is if G hat is discrete quantum group, then sister reduced G hat admits weak expectation if and only if he had them. So in the classical settings, we have the same kind of idea. So this if my gamma is a discrete group, then it is amenable if and only if it's reduced group sister algebraic weak expectation property. But there we have this triviality condition, which helps us to prove this. But this is true for the whether it is CAC type, non-CAC type, no matter. It is because we have this condition. It will immediately tells you that this is true. So this is the main thing is happening here. So I mean the proof, it's basically we have to get this condition, but I don't think I have enough time to okay, so yeah, that's the main idea. So but I should also talk about some cross product, but I don't have enough time, so I should stop here. So.
Thanks very much, Arnab. Do we have questions from the audience in person or online?
I have a question that might make me sound stupid, but I don't mind. Isn't the case sometimes the L infinity of G is a factor? And does that mean that none of those compact quantum groups are co-amenable?
Yeah, in that case, maybe the quantum injectivity may help something. I mean, I don't know, I mean, how to answer your question, but so we have this definition for weak expectation. So there is another definition of quantum injectivity, which gives you how these two guys, so this guy and this amenability condition are compatible with each other. But this injectivity, compact injectivity condition is, we thought it's quite heavy condition. So we try to down the condition to get some amenability condition for here, and that's why we use this, because you are asking factors, so maybe the injectivity condition might express.
Do you have any other questions? That doesn't appear to be the case. We'll thank Arnab again. And so now we